Hello, today our topic is physics-informed neural networks for blood flow simulation. Simulation of hemodynamics is essential for understanding how heart and blood vessels function under various physiological and pathological conditions. There are several ways to simulate blood flow. The most famous are computational fluid dynamics and Lattice-Boltzmann method. Both of these methods are widely used, but they are really costly in computation and hardly scalable. So the solution for this task is physics-informed neural network, which are just the neural networks which has the complicated loss function, which includes differential equations. So here you can see the architecture of physics-informed neural network. Here it's just normal input, normal neural network with hidden layer, input layer, output layer, and what is interesting, look at the loss function. Here there are two equations, the boundary and the data equation. Here they are like in general form, but for our task, for blood flow simulation, there should be specific. So our object of research is here. You can see this is an abstract picture of aorta. Here the blood circles represent the blood cells, and the gray tube is some kind of artery, aorta, some vein. On the picture C, you can see the big sphere. It's not tennis ball, it's just aneurysm, some kind of deformation of veins. So now our goal is to get from this picture to get this picture, the simulation which includes the blood velocity, the blood movement, and here you also can see the comparison of pins and CFD. These methods perform quietly the same, they provide the same results. The blood is a fluid, so for us it will be really useful the Navier-Stokes continuity equations. We have several assumptions of flow type, unsteady flow. I should notice that we in our presentation we do not take into account the blood flows with some pathological conditions such as aneurysm, such as blood clots, just simple blood flow simulation in arteries. So since our blood flow is incompressive, which means it doesn't contain blood clots, the continuity equation is expressed like this. So then we are going to the equation of motion. For us, since the blood is liquid, it will be the Navier-Stokes equation for incompressible fluid stock. So look at this. Here u will be the velocity vector, t is the time. I should notice that we are talking about 4D space. We are considering x, y, z coordinates and moreover the time. Then rho is the fluid density, p is the pressure, and it's just a physics equation. Additionally, we need to consider Reynolds number. In arteries, because of the Reynolds number often remains below the critical threshold, the 1000, and sometimes it can be even less than 1000 in small arteries, because small arteries has smaller diameter, slower flow rate. The flow is typically laminar under normal physiological conditions. However, in certain pathological conditions or in larger arteries with higher flow rates, the Reynolds number can approach or exceed the critical value, leading to the turbulence. So the most important thing is loss functions. Here you can see loss function PDE. A loss term derived from the residuals of the partial derivative equation. Then you can see here the loss which is defined by boundary conditions, and here a loss term which is calculated based on potential available space measurement data. The PDA equation represents the mean squared residuals of the PDA accessed and NPDA randomly chosen points within the same geometrical space. Similarly, in this equation, the boundary loss is accessed by considering randomly selected points along the boundary of the geometry, and the n data points denote the locations where the solution U may be available or measured. All these loss functions are considered in the main loss function, and they are assigned with weights, so the specific neural network can be adjusted based on these weights. So let's consider the neural network, especially for the blood flow simulation. I should notice that this architecture of neural network, like the usual one, is not the only way to create physics-informed neural network. The modern research include graph neural networks and some kind of recurrent neural networks for blood flow simulation. So here, as you can see, XYZ, three-dimensional space and time. So the total dimensionality is 4. Then the normal neural network, and here look at the loss functions. As you can see, here is LPDA, which means partial derivative equation loss, which considers conservation of momentum and conservation of mass, boundary loss and measurement loss. All these losses are combined in the one total loss functions, which this neural network tends to minimize. You can ask me a question, how can be calculated the loss here? Actually, there are several approaches. For example, the one way is to use numerical approach to calculate the gradient. However, sometimes the gradients can be computed manually, but this approach is more costly by computations. What are the results of blood flow simulation artery? Usually, researchers interested in the velocity and in the pressure inside the artery. As you can see here, you can see the graph of blood velocity. Also, here you can notice some parameters. For example, also you can see here some parameters. For example, beats per minute here, and RR parameter, which is defined by the time before 2 heartbeats. One more example of results of blood flow simulation is different kinds of plots with different kinds of velocities of blood in arteries. Thank you for your attention. Что там calculate? Не знаю. Thank you for your attention.